Hi everyone, welcome to Cram for Chem, where I help you study as much chemistry as possible in a short amount of time. In this video, let's talk about electrons. We'll go over the organization of the periodic table, electron configuration, orbital notation, and photoelectron spectroscopy, or PES. The periodic table is a chemist's most important tool because it contains a wealth of information about every element. Let's first look at how it's organized. The rows on the periodic table are also called periods, and they represent energy levels. For example, hydrogen and helium are both in row 1, so they both have 1 energy level or 1 electron shell. Any element in row 2 will have 2 energy levels or 2 electron shells, and any element in row 3 will have 3 energy levels or 3 electron shells. The columns on the periodic table are called groups or families. The group number represents how many valence electrons or outermost electrons an element has. For example, both hydrogen and lithium are in group 1, so they both have 1 valence electron. This is how groups are numbered on the periodic table. Notice that this middle block is skipped. That's because these are the transition metals, and they don't follow the same pattern as the main group elements. Because valence electrons are what decide the charges and chemical properties of elements, all elements in the same group have the same charges and properties. These are the charges for every group. The reason these charges are what they are is because of the Octet Rule, which states that all atoms want to have a full valence shell. This means that hydrogen and helium want to have 2 valence electrons, and all other atoms want 8 valence electrons. Between gaining and losing electrons, elements will do whatever is easier to get them to a full shell. Elements in groups 1 through 3 will lose electrons and become positive. Elements in groups 5 through 7 will gain electrons and become negative. Group 4 elements can either gain or lose. Group 8 elements are called noble gases because they have a full valence shell, so they don't need to gain or lose electrons, and therefore they will not react with other substances. Groups 1 and 7 are very reactive because of how close they are to a full shell. Let's look at this atom from group 1. A group 1 element will react to lose this 1 valence electron. Here's an atom from group 7. It will react to gain 1 more electron. Electrons are organized into orbitals. Orbitals are regions with a high probability of finding electrons. Different orbitals have different shapes. The s orbital is a sphere, and the p orbital is dumbbell-shaped. There are 4 different orbitals, and they correspond to different regions on the periodic table. They are the s, p, d, and f orbitals. Notice that helium also belongs to the s block. We use something called electron configuration to show the distribution of an atom's electrons through the different orbitals. Basically, we want to know how many electrons an element has and how those electrons are organized into orbitals. This is how electron configuration is formatted. The big number in the front is the energy level. The letter is the orbital type, and the superscript number at the top is how many electrons are in that orbital. Let's practice writing the electron configuration for different elements. Electron configuration is very easy as long as you remember this. Follow the order on the periodic table. Let's write the electron configuration for nitrogen. Always start with element number 1, so hydrogen. Then you'll read the periodic table in order until you get to your target element. Hydrogen is in row 1 s block, so I'll start by writing 1s. To get to nitrogen, I have to read through hydrogen and helium, so I'll write a superscript 2 to show that I'm going through 2 elements that both belong to row 1 s block. Then I go to row 2 s block. I have to read through 2 elements in 2s, so I'll write 2s2. Then I get to row 2 p block, and I have to read through 3 elements in 2p to get to nitrogen, so I'll write 2p3. The electron configuration is 1s2, 2s2, 2p3. If your element is further down on the periodic table, electron configurations can get pretty long, so there's a shorthand notation. It's called the noble gas configuration. What you do is you start your electron configuration with the noble gas in the row above. Let's do chlorine as our example. Here's chlorine on the periodic table. We'll go to the row above and find the noble gas, which is neon, so I'll start by writing the symbol for neon in brackets. Then I continue my electron configuration as usual. I'll follow the order on the periodic table to row 3 s block and write 3s2. Then I keep going until I get to chlorine, so that's 3p5. This is the shorthand notation for chlorine. There are special rules for the d and f orbitals that you should know. When you get to the d orbital, the energy level will be the row number -1. For the f orbital, the energy level will be the row number -2. Let's practice with arsenic. I'll do the noble gas configuration, so I'll go to the row above. The noble gas is argon, so I'll write Ar in brackets, then 4s2. When I get to row 4D block, instead of writing 4d10, I'm going to write 3d10. Then I get to the P block, and it'll be back to 4p3. Another way of representing electrons in orbitals is with orbital notation. It shows electrons as arrows and orbitals as boxes or lines. Let's look at this electron configuration. If I want to convert it to orbital notation, I'll set up my orbitals like this. I have the 1s, 2s, and 2p. The number of lines is the total number of electrons possible for that orbital divided by 2. For 1s, since it has 2 electrons, I'll draw 2 arrows, one up and one down. Same thing for 2s. For 2p3, I'll spread out my 3 arrows, so 1 up arrow on every line. You might also see this drawn vertically. The higher up you go, the higher the energy level is. There are some rules you have to follow when you draw your electrons in orbital notation. The first is lower energy levels fill first, so go in the order from the periodic table. 1s gets filled first, then 2s, then 2p. When there are degenerate or same orbitals, that's when you see multiple lines for the same orbital, don't pair electrons until each orbital has 1 electron. Spread them out. Finally, electrons must have opposite spins, which means the arrows on the same line need to face opposite directions. You can't have 2 up arrows together or 2 down arrows together. Sometimes you might come across electron configurations or orbital notations that do not fill orbitals in order. This is when you have excited electrons. Let's look at this example here. The 2s orbital isn't filled yet, but there's already an electron in the 2p orbital. This 2p electron is called an excited electron. If that electron moves back to where it's supposed to be and the orbitals are filled in order, we say that the atom is in the ground state. The next thing I want to talk about is how electrons closer to the nucleus feel stronger attraction to the protons, so they are harder to remove from the atom. This leads us to something called Photoelectron Spectroscopy, or PES. On a PES, you'll see all the electrons of an atom graphed according to how much energy it takes to remove them. Each peak represents a different orbital. When you read a PES, you want to find the highest energy side. The peak closest to that side represents the orbital closest to the nucleus, which is the 1s orbital. On this PES, this peak has highest energy, so it is the 1s peak. Then we have 2s and 2p. Next, the height of each peak represents the number of electrons in that orbital. On this PES, we have 1s with 2 electrons, then 2s2 and 2p4. This is the electron configuration for oxygen. Let's look at another PES in comparison. This purple PES is almost identical, but its 2p peak is a little higher, so its configuration is 1s2, 2s2, 2p5. This is the PES for fluorine. You might notice that fluorine's PES is shifted a little to the left compared to oxygen's. That's because fluorine has higher nuclear charge, which means it has more protons. As a result, it has higher proton-electron attraction, so all of its electrons take a little more energy to remove. I hope this video was helpful. Thank you so much for watching, and I hope to see you in the next one.